Our next goal is the Pythagorean theorem on the hyperbolic plane. But before we get there, we need some auxiliary result. First, let me just remind you the definition of hyperbolic sine and hyperbolic cosine. So I'm just going to write it here, but quickly erase. So the hyperbolic sine of x, the sinh of x, is defined as e to the x minus e to the minus x over 2, while the hyperbolic cosine is e to the x plus e to the minus x over 2. And then the hyperbolic tangent is just the hyperbolic sine over the hyperbolic cosine. You will see that the hyperbolic functions actually play a similar role to the standard trigonometric functions when we talk about hyperbolic plane. So it's actually easy to, very easy, I'll leave it to you to see what happens when you take cos squared x and subtract sinh squared x. Remember the formula for the standard trigonometric functions is cosine squared plus sine squared is equal to 1. So cos squared minus sinh squared is equal to 1. All right, that's a very easy calculation. Just square this, square that, cancel like terms, and you get this formula here. Okay, so 2 can then be derived from knowing sinh, right? Because if you know sinh, you also know cos using this formula, for example. And then the hyperbolic tangent is just the ratio of these two. So you see this formula is just the ratio of these two formulas. So really the only thing to prove will be this formula here. And what is this proposition that we're trying to prove? It's the following. So let AB be about geodesic segment somewhere on the hyperbolic plane. As you know, the geodesics can be classified as either vertical lines or arcs of circles centered somewhere on the x-axis. So when I say about geodesic, I mean an arc of a circle centered somewhere on the x-axis. So let AB be such. So A is like the beginning of this arc and B is the end of this arc. And let AE and BD be vertical geodesics stemming from A and B respectively, right? So the situation is kind of like this. Here's about geodesic. And so these are the vertical geodesics. And if I denote by C the distance, the hyperbolic distance between them, then these formulas give me the length of this segment in terms of the angles alpha and beta. So what are the angles alpha and beta here? So here the angle alpha is just the hyperbolic angle. So it's just the same as the Euclidean angle, but so that's the angle between so I'm going to write it like this, AEAB. So this is not a straight line segment. By this I mean the hyperbolic geodesic. And the same thing here, hyperbolic. It's the hyperbolic geodesic, so it's an arc between A and E, and it's an arc between A and B. In fact, A and E is just a straight line, right? Because that's a vertical geodesic, but AB is an actual arc. And what's beta? Similarly, it's the angle between AB and BD. Okay, so in other words, these are sort of these two angles here. Okay, so let's get to proving this proposition. So this allows you to express the length, to find the length of a bout geodesic in terms of the angles this bout geodesic forms with vertical lines. So first, we're going to cover a special case of it. So, proof. First assume that beta is 90 degrees. Okay? And so now I can finally refer to this picture that was on the board from the beginning, because that's the picture for this special situation. So A and B are 2 points on the hyperbolic plane. And this bit here, so I'm even going to erase that part to just not confuse you as to what the C refers to. So this bit, maybe I'll just draw it like a dotted line here. So this is part of a circle centered at the point C. So let's see on the x-axis. So B the center. Of the bout geodesic. AB, you know that bout geodesics are parts of circles centered on the x-axis, so that's a point somewhere on the x-axis. So let's call it C. Okay, so that's the bout geodesic, and its length is denoted by C. And now, AE is this vertical line over here that starts from A, and BD is the vertical line over here that starts from B. And because of my simplifying assumption that beta is pi halves, you see that this is a right angle here. So in other words, this circle actually reaches its highest point here, and then keeps going, and then goes down, right? Because we're in this special situation when beta is equal to pi halves. Okay, so now the statement is, the claim is that the sinh of C is equal to cosine alpha plus cosine beta divided by sine alpha sine beta. So let's actually, so let's prove this. So then, if I take 2 sinh C, then that's by definition e to the C, e to the minus C. Now, I already know how to compute length of geodesics, right? I know, actually. So we know, so let me just change the color. So we know that the length C is equal to natural log, and now I need some cosecant of some angle minus cotangent of some angle divided by cosecant of some angle minus cotangent of some angle. All right, what are these angles? Well, because I go from here to here, the angles are alpha and this angle here. So, why is this angle alpha? That's again the same principle that the angle between a vertical geodesic and a bout one is the same as the radius of the circle forms with the x-axis. It's like in the previous video, again the same idea that the tangent line to the circle is perpendicular to the radius. So if you just look at this, then this angle is equal to that angle. So I know this angle is alpha here. And then how do I compute the length of a geodesic between 2 points? That's natural log of cosecant of this angle, the left endpoint, minus that angle. So it's, in this case, it's 90 degrees in both cases. So it's pi over 2 minus pi over 2 divided by cosecant alpha minus cotangent alpha. Okay, that's just a formula we derived earlier for the length of such a bout geodesic. Okay, but pi over 2 is a special angle. So what's cosecant of pi over 2? That's 1 over sine. This is 1 over sine pi over 2, and sine pi over 2 is 1, so this is 1. On the other hand, cotangent of pi over 2, that's cosine over sine, so that's 0. Okay, so this C here is equal to really natural log of 1 divided by cosecant is 1 over sine alpha minus cosine alpha over sine alpha. So you see that that's natural log of sine alpha divided by 1 minus cosine alpha. Okay, so this I can feed into this formula here for this sinh, so I'll erase the statement here, but leave the formula that we're trying to prove. This 2 sinh C is equal to, well, E and natural log cancel each other, so that's sine alpha divided by 1 minus cosine alpha minus, again, E and natural log cancel each other, but this is, right, this is the same as 1 over e to the c, so it's the reciprocal of that. So we get that formula. Now this is already telling you, this already gives you some expression for C, or for sinh C, in terms of just this angle alpha. But let's actually get it in a slightly nicer form. So what do we get? It's just algebra and trigonometry. 1 minus cosine alpha. Sine alpha will be a common denominator, so then here I get sine squared alpha minus, and here I get 1 minus cosine alpha squared. So that gives us what? 1 minus cosine alpha sine alpha, sine squared alpha, minus 1 plus 2 cosine alpha, minus cosine squared alpha. Okay, now, standard trigonometry, right? This is just minus cosine squared alpha. 1 minus sine squared alpha is cosine squared alpha. So sine squared alpha minus 1 is minus cosine squared alpha. So I have 2 cosine alpha and then 2 cosine squared alpha. So it's 2 cosine alpha minus 2 cosine squared alpha divided by 1 minus cosine alpha sine alpha. So I can take out 2 cosine alpha and I get 1 minus cosine alpha divided by 1 minus cosine alpha sine alpha. So all I get is, and then these two things cancel, so I get 2 cotangent. 2 cotangent alpha. Okay, so going back to, so I don't need these formulas over here. So as a conclusion, I get, so that was 2 sinh. So sinh C is equal to cotangent alpha. If beta is equal to pi halves, that was our assumption. Just a quick check that it actually does give you this formula for this special case. When beta is equal to pi halves, sine beta is equal to 1. So that's only the sine alpha in the denominator. And cosine of pi halves is 0. So you really get cosine alpha divided by sine alpha. So indeed you get cotangent alpha. Okay, so how do you now get the general case from this? So we will now deduce the general case from this. So for this we need to change the picture a little, and namely I am just going to do a little change here, namely, so remember that means the angle beta is no longer straight, it's no longer right, so that means I'll take this away, the notation. Oh, C is still here. So my point B will be somewhere else. Let's say somewhere here. And the point D will lie above it. Okay, so here. Not a very good picture. Still not a very good picture. Trying to draw a straight line, very difficult to do it in this corner. Okay, there you go. All right, so let's correct all this. So erase this. This is irrelevant for us for now. Kind of irrelevant. You'll see it's not that as irrelevant as it may seem. All right. So that means my angle beta is here now. Okay, so we are in this general situation. You see, it's no longer necessarily a right angle. So alpha and beta are sort of arbitrary angles here. But I still want to leave this picture here because I want to use this property that we just proved to prove the general case. So let's erase this and all this calculation here. And I kind of want to reintroduce this point. So I'm going to call this point M. So let's actually write down some words so we see what's going on. So this is point E. And this is that. So now let A, B be an arbitrary position. And I'm going to, so there's sort of two cases here, but I'm going to only cover one case here. So let M be the point so remember AB is still, so this is B here, right? AB is still a circle because it's a bound geodesic that connects the points A and B. So it's still a circle, so it has some center. So maybe let's just say that again. So let C be the center. Be the center of the bound geodesic. A, B. Now remember, we're not assuming that A is above B, right? We said that in the statement of the proposition that that the geodesic connecting A and B is about geodesic. So we definitely we're not in the situation where A is on top of B or B on top of A. So there really is a circle that connects them and it's centered somewhere here. So we already know the definitions of alpha and beta. But now let M be the point on that circle, be the point on that geodesic with largest possible y coordinate. Right? This is a circle, so I'm picking it to be the north pole of that circle, at the top of the circle. So there are essentially two cases where M is between A and B and when M is not between A and B. So we're going to now talk about the case when M is in between A and B. So we will prove the claim in the case when M lies on the segment AB, on the geodesic segment AB, on the geodesic segment AB. So I'll leave the other case for you to think about. Why do I do this? Oh, because then, I'm introducing here two right angles. So I will try to use the previous case and sort of do this in two pieces, in two portions. So I'm going to denote by C1 this length from A to M, and C2 the length from B to M. So let C1 be the hyperbolic distance between A and M, and C2 be the hyperbolic distance between B and M. then C is equal to C1 plus C2. Okay, so maybe I'll just continue down here. So sinh C is equal to sinh C1 plus C2. Okay, and I'm going to now use a hyperbolic trigonometric formula that I am not going to prove. You can find the proof in many sources, or you can just try to prove it yourself. It's proved essentially, again, from the definition of sinh. So, sine of alpha plus beta is sine alpha cosine beta plus sine beta cosine alpha. So, something similar actually holds here. So the formula is that's sinh C1 cosh C2 plus cosh C1 sinh C2. So essentially exact analog of what it is for the standard trigonometric functions. Okay. But if I now look at C1 and C2, C1 is the about geodesic from the first case of the theorem, where one of the angles is alpha and the other one is 90 degrees. So we have sinh C1 to be cotangent alpha. And cosh, what do I want now? Sinh C2 so we are now in this situation here. Well, that's going to be cotangent beta. Using so then one computes that the hyperbolic cosine of C1 is actually equal to cosecant alpha, and the hyperbolic cosine of C2 is equal to cosecant beta. Okay, again, there is a relationship between cosh and sinh that we wrote down here. So once you have sinh, you can actually compute the cosh and vice versa. Okay, so once you have that, what do we get? So sinh C is equal to, okay, so let's see, so that's sinh C1, so that's cotangent alpha, cosh C2, so that's cosecant beta, plus cosh C1, so that's cosecant alpha, sinh C2, that's cotangent beta. So what is this? So cotangent, that's cosine alpha over sine alpha, cosecant is 1 over sine beta, plus 1 over sine alpha, cosine beta over sine beta, which gives 1. Which gives 1. Okay, so again, a little summary of this. So we're looking at a general situation where these angles are not necessarily equal to 90 degrees, but if the top of the circle happens to be between these 2 points A and B, then we can split this arc into 2 arcs. And now, to find the length of this arc C, that's just the sum of the arc length C1 and C2. So sinh of C is equal to sinh of C1 plus C2, and then we use this trigonometric formula to get it into sinh C1 cos C2 plus cos C1 sinh C2. Okay, and now for the sinh, we just use what we proved, because for sinh C1, we're in this exact situation as we're in part 1, when none of the angles is right, so we get sinh C1 to be cotangent alpha. And the similar situation happens here, right, where so we have, I mean, it doesn't matter here, but that's the angle beta. So again, it's this situation where one of the angles is right, so we get that sinh C2 is equal to cotangent beta. How do I get the cos C1 and cos C2? Well, again, that's the relationship, right? That cos squared minus sinh squared is equal to 1, so you can actually compute 1. You can compute the cos once you have the sinh. And I'm not doing the calculation here, but it's cosecant alpha and cosecant beta. So once you have that, you just plug it into the formula and you get this general formula.